Well, hello world. Give me a wave if you can hear me okay. All right, seeing some waves. Welcome to our Zoom audience here. We're going to be filming CS50's second lecture in our Introduction to Programming with R. My name is Carter Zenke, and this is
David Malin. Nice to see everyone again.
Now, we usually begin with a souvenir photo, so I invite you all to turn on your cameras and start smiling. And our colleague Rong Shin will soon swipe through all of our Zoom tiles and take pictures of us smiling and waving. So I'm going to count to 3 and make sure to smile and wave. 1, 2, 3, and let's smile and wave. Hello, hello. Nice to see so many folks from all around the world. Keep smiling and keep waving for just a little while longer.
Can I make a special shout out to one person?
Go ahead.
Special shout out to CS50's own Brenda Anderson, whom I see in the chat here, who's awake all the way in New Zealand with us today. So if you see Brenda in the chat, she's indeed on the team here too.
And are we go to a souvenir photo or still going? All right, we're good. Okay, no, it's okay. All right, so we're going to come back in about 5 minutes to actually officially begin the lecture. But just so you all know beforehand, it's supposed to be interactive. So certainly feel free to ask questions in the chat or raise your virtual hand via Zoom so we can call on you and you can ask your questions live. But other than that, we'll see you all in a few minutes. Well, hello, one and all, and welcome back to CS50's Introduction to Programming with R. My name is Carter Zenke, and this is our lecture on transforming data. We'll see how to remove unwanted pieces of data, how to subset our data to find pieces of it we're interested in, and how to ultimately combine data sets from different sources into one big data set. So let's go ahead and jump right on in. Now, whether or not you're familiar with statistics or data science, you might have heard of this idea of an outlier, where an outlier is some piece of data that falls outside some standard range. Now here, for example, I have a chart representing the average daily temperature in January up here in the Northeast United States. Notice first, on the y-axis here, I have temperature in degrees Fahrenheit, 'cause that's what we use up here in the US. And then down below, on this x-axis, I have days of the month. And so it seems like each bar here represents one day in January, and how high or low that bar goes represents the average daily temperature on that day. Now, up here in the Northeast US, it tends to get pretty cold, all the way down to like 0 degrees Fahrenheit, usually. But it could go as high as, let's say, about 50 degrees Fahrenheit. Now, that's our standard range for temperatures. But you might notice, looking at this graph, there are a few bars that fall outside that standard range. Like if I look down here on day 2 of January, it seems like this is a pretty cold temperature, somewhere like -10, -15 or so. Day 4 seems to be even lower, like maybe -20 or thereabouts. And then day 7 seems to be maybe higher than 60 degrees. So these are what we would call outliers. They fall outside of the standard range of temperatures we would expect to see. Now, in your analyses, you might choose, for one reason or another, to omit these outliers, to remove them, and we can actually use R to do just that. So let's go ahead and go back to our old friend RStudio and begin working on this problem here. I'll come back to my computer, and let me open up RStudio, which was, remember, we called this our IDE, our Integrated Development Environment, to work with R code and to write our own R programs. Now, we saw this function called file.create last time that allowed us to create. Yeah.
Sorry to interrupt the version numbers there. Did you apply the CSS?
Oh. I thought I did, but I just updated RStudio because they made a new version. So let me remove that. All right, we'll come back in a few minutes so we can remove the version number here. Well, hello one and all, and welcome back to CS50's Introduction to Programming with R. My name is Carter Zenke, and in this lecture, we'll learn all about transforming data. We'll see how to remove unwanted pieces of data, how to subset our data and find certain pieces that we want to take a look at, and ultimately how to take different data from different sources and combine it into one single data set. So let's go ahead and jump right on in. Now, whether you're familiar with statistics or data science, you might have heard of this idea of an outlier, where an outlier is some piece of data that falls outside some standard range. Now here, for instance, is a graph of average temperatures in January up here in the Northeast United States. Notice first on the y-axis, I have the temperature in degrees Fahrenheit. That's what we use up here in the US. And then down below, I have the day of the month, 1 through 31. And it seems to me like these bars represent individual days of the month, and how high or low they go represents the average temperature on that day. Now, in the Northeast US, it can get pretty cold by default, kind of all the way down towards 0 degrees. But it could also get as warm as, let's say, 50 degrees or so. It's kind of shown by most of these bars. But in this data, it seems like there are a few days that fell outside of that range. Like if I look down here on day 2, that seemed like a really cold day, somewhere like -10, -15 degrees. Day 4 seemed even colder, like -20 or so. And then day 7, that was really warm for January up here. It was like 60 degrees or higher. So it seems like these would be the outliers in this data set of temperatures. And for one reason or another, you might hope as a scientist, a data scientist, or a statistician to remove these outliers altogether and conduct some analysis without them involved. So let's see if we can solve this problem of outliers now using R. We'll come back over here to RStudio, our old friend, our IDE, or our integrated development environment that allowed us to write R code and to write R programs. So we saw this function last time called file.create that allowed me to create a new file in which I could write some R code. So I'll go ahead and type that same thing here, file.create. And in this case, I'll call this one temps.r for temperatures here. And I'll hit enter. And now I see true, again, which means this file was in fact created. And as we saw last time, I can go to my file explorer over here, which shows my working directory, the place I'm going to store these R files by default. And I can click on temps.r to now open it in what's called my file editor, where I can write more than one line of R code. Now, as we saw last time, one thing you'll often want to do in R is read some data from some file. And we saw these CSV files, comma-separated value files that could store tables of data. Well, it turns out that R can also work with all kinds of other file formats, one of which is particular to R. This is called a R data file. And it turns out that using an R data file, you can store R's data structures, like vectors, data frames, like we saw last time, in a file itself, such that when I load them, I just see exactly what was in the environment in terms of that same vector or that same data frame. So let me try doing that, and to load an R data file, I can use this function conveniently called load. So I'll type load here, followed by some parentheses, and now I could type the name of the R data file I want to open. Now my colleague, let's say, has given me a file called temps.rdata, so I could open it using load temps.rdata, just like this. And now let me run this line of R code. I can do so if I type Command-Enter on a Mac or Control-Enter on Windows. I could also click this Run button here. Let me hit Command-Enter, and I'll see, well, nothing really. But if I look in my environment now, if I open this other pane over here called Environment, I should actually see that I now have a vector called temps that seems to have 31 numbers as part of it here. So why don't I try to find, first off, the average temperature in all of January. And if I want to find an average, I could use this other function called mean, where I often call an average a mean. Well, I could type mean here and then give it this same vector temperatures. And if I run this line of R code, I'll hit enter and see the mean, the average of the temperatures, was 22.74 roughly degrees Fahrenheit. Now, if you're not familiar with averages or means, all I've done here is I've summed up all the values in this vector, and I have divided by the number of values that I have, producing some kind of typical value of the data set, also called the average. So this then tells us that in January, it seems like our average temperature is somewhere around 22 degrees Fahrenheit. But that's not why we're here. We're here because some of these data points seem to be a little anomalous. We had some really cold days and some really hot days, and maybe we want to remove those days altogether before we run this temperature analysis. So let me actually take a peek at this entire vector. I can do so by simply typing the name of the vector and hitting Command-Enter to see it down in my console. And here are each of those 31 values. So one thing you might notice is that I can see these outliers now in the data below. It seems like that second day that seemed really cold, well, that day actually had an average temperature of negative 15 degrees Fahrenheit. And that fourth day, that was about negative 20 degrees. And same thing here, it looks like the seventh day was all the way up at 65, which is pretty warm over here. So one thing I might want to do is actually pull out these outliers to use them in my code. And we saw last time I could use this method of indexing into this particular vector that is trying to find particular values and pull them out to use in my code using their positions in this vector. Now it seemed like that second day was particularly cold, so I could find that temperature by using temps bracket 2, where 2 represents that second element in our vector. If I want to find it, I could use bracket 2, and I'll see, in fact, I get back negative 15. Same thing for the other one. I could use temps bracket 4, and that shows me negative 20, that other outlier in our data set. I could also use temps bracket 7, and that would show me this really warm temperature overall in this same vector. But this is where we left off last time, and what I want to do now, ideally, is not have these outliers represented individually, but really have a vector or a list of those outliers to work with. And I'd argue that I don't quite know how to do that just yet, but I can show you one trick we can use in R to get back a vector from a current vector. So let's think through what we've already done. We saw last time if we wanted to get some element from a vector, we could use this same bracket notation that we even just now used. I could use bracket notation and say, give me the second element inside of this temps vector. And this is known as indexing into this vector. I take the position of the element I want to find, put it in brackets, and I get back that very same element. So again, temps bracket 4, negative 20, temps bracket 7 is now 65, but it turns out that cleverly in R, we don't always have to provide a single index. If we want instead a vector from this current vector, maybe a vector that includes only some values, well, I could actually give as the index, not a single index, but a vector of indexes. And I could actually index into this vector using a vector of indexes. So let's take a look at that. I could instead type something like this. Give me 2, 4, and 7. Those elements at these positions, 2, 4, and 7. And notice here I'm using this C function we saw earlier, which stands for combine. This makes for me a vector that includes 2, 4, and 7. And now I'm indexing into temps using not a single value, but a vector of indexes. And what I'll get back is as follows. I'll kind of mark these as the ones I want to grab, and I will grab them out and turn them into their own vector for me to work with in R. So let's go ahead and try this transformation of this vector in R and see what we get back. I'll come back to my computer, and I'll go back to RStudio where we have our same temps vector. But now I don't want these individual values. I want a vector of the outliers. So I could modify how I'm indexing into this temps vector, and I could use instead a vector to index into it. I want to get back those values at locations 2, 4, and 7. And if I hit Command-Enter here, I'll see I now have a vector of those outliers. And that's pretty cool. I think we do a lot with this. But one thing I haven't done yet is removed them. Like if I still look at temps now, I'll see that those vectors or those elements are still part of my vector. I haven't kind of taken them out to remove them altogether. If I wanted to do that, well, I'll need to take a different approach. And one thing I can do in R is use a simple minus sign or a dash and prefix my C function here, my vector of indexes. And what this will tell R is, I don't want you to grab these. I actually want you to remove them. This minus sign says take the elements at these indexes and drop them, remove them from this vector. So now if I run this line of code on line 3, what do I see? well, all of my temperatures, but you'll notice that I'm now missing some. I'm missing those elements that were previously at positions 2, 4, and 7, or those outliers. So let's visualize this too. One thing that I've done over here is I've said, I actually want you to remove these values. And I've done so by putting this dash in front of this particular index, this vector of indexes here. And what R will now do is highlight these essentially and say, OK, I know you want to remove these particular elements. And it will then return to me, give me back a vector that includes not those elements anymore. It becomes shorter, so to speak, just like this. So now, back in R, I'm able to remove those elements from my vector. Now let's come back over here and let's see what more we could do with this. Well, one thing I wouldn't want to be in this scenario is the person who has to go through and find all of these particular outliers and tell me what their indexes are. Like if I had to go through thousands of pieces of data and figure out which ones were the outliers and which ones weren't, well, I'd kind of be wasting my time. What I'd love to do instead is really ask a question. Is this piece of data an outlier, or is it not? Ask this yes or no question. And it turns out that in R, we can actually express those kinds of questions using a tool called a logical expression. A logical expression. Now, a logical expression allows us to, as programmers, to express these yes or no questions and get back a yes or no answer. In particular, logical expressions often use what we're going to call comparison operators. And here are a few of them here. Notice this one, this double equal sign, stands for equality. It allows me to compare two values, a left one and a right one, and ask, are they equal or are they not? Now this next operator, this exclamation point equals, that stands for not equals. It will take a value on the left and a value on the right and say, are these two values not equal? And similarly for the other one down here, you might have seen this greater than sign in grade school. This one stands for greater than. This one stands for greater than or equal to. This one less than or equal to. But these comparison operators allow us to compare different values and get back a yes or no response. And actually true to their name, these logical expressions return to us what's called in R a logical, where a logical is simply this value that is either true or false, yes or no. And so you'll see these values occur throughout your time in using R. Capital T, R, U, E, and capital F, A, L, S, E. These represent yes or no, true or false. Is this comparison true or not? Now you might also see them in terms of just T and F. This is like shorthand for these same logicals. But in general, you might often see true or false here. So let's see if I could use these logical expressions to make my job a whole lot easier now as a programmer. I don't have to find these actual indexes going through data one by one by one. I'll come back to my code over here. And why don't I go back to RStudio. So here I have these indexes that I found by kind of combing through my data. But it would be nice if I could have R tell me whether some piece of data is an outlier or not. Well, one thing I can do is maybe try to find those temperatures that are lower than we'd usually see, like less than 0 degrees. Below 0 degrees is kind of this common benchmark for it was really cold. So let's look maybe first at the first element in this temps vector and ask the question, was that temperature lower than or less than 0 degrees? And this is my first logical expression. Now, if I were to run this line of code, hit Command Enter here, what do I get back? Well, false. So it seems like temps bracket 1, if I were to run this and show you what that actually is equal to, 15. 15, of course, is not less than 0. Now, what if I did it for the second one? I could ask that same question, temps bracket 2, and then I could say 1 over here, and now I have true. So it seems like temps bracket 2 is negative 15. So in that case, actually, let me change this. This is not 1. It should be less than 0. So temps bracket 2 less than 0. Negative 15 is certainly less than 0. I could keep going and ask the same question for temps bracket 3. Is temps bracket 3 less than 0? Well, turns out it's not. If I see temps bracket 3 down here, looks like that value is 20. So I've gotten some of the way there. I'm able to ask these questions of individual pieces of data, but I'd argue my job, my life isn't that much easier right now. I still have to go through all of these indices, temps bracket 4, temps bracket 5, and so on, and my job is still to write lots and lots of our code to ask these questions. Now, thankfully, these comparison, or these operators here, they allow me to actually give an entire vector as input. They're what we would call vectorized. So I could, on line 3, instead of giving a single value from this vector, I could give it the entire vector and get back a vector in response. I could run line 3, Command Enter here, and now I have a whole vector of true or false values, these logical values. This is what's called a logical vector. And notice here that for every element inside temps, I actually asked this same question. Is this element less than 0? Is this element less than 0? And I see it seems like the second and the fourth are less than 0, just like we saw in our data. So let me pause here and ask, what questions do we have on these logical expressions and these logical comparison operators? I think we're pinning to the wrong screen. Yeah. Ahmed?
Can I access a tuple in the list?
Do you mind repeating that for me one more time?
Can I access a tuple in the list in temps? If I added a tuple in the list of temps, can I access it?
Gotcha. So I think you're asking about a tuple, where a tuple is often used in other languages to represent some list of values that is kind of fixed and can't be changed. R, I believe, doesn't have that same kind of idea, so not quite as applicable here. You could, though, have a vector of vectors, which I think would get closer to your idea of a tuple in programming. But a good question there. Other questions on these logical expressions or these comparison operators? Let's go to Luis.
When you use the deletion minus operator, is that affecting our source data?
Can you repeat that one more time for me? Sorry.
When you used the deletion operator with the minus sign, is that modifying our source data?
Good question. So when I used that negative and I got back a vector that excluded some values, the question is, did that kind of save as a new vector? Did it change our environment at all? And the answer is, I get to decide that myself. If I go back to my code over here, let me go back to what we did before, where I had temps here as a vector, and I decided to, in this case, access individual elements of it, like 2, 4, and 7. I instead wanted to remove those. If I wanted to actually update temps to remove those in future lines of code as well, I would need to reassign this vector. I would say temps is reassigned, in this case, the exclusion of these particular indexes here. So I'm first going to remove these elements, 2, 4, and 7, and reassign it back to temps. And now, below this line of code, temps will always exclude those values for me. A good question. OK, so we've seen how we can ask these questions in our code to determine which of these values are outliers. And in fact, we can use these logical vectors, these logical expressions, to actually figure out automatically at which indexes we had these particular values being true or false. We can use a function called which, where which takes as input this vector of logical values and tells me which ones are true, or more particularly, it tells me the indices of which ones are true. Here I'll run line 3, and I get back both 2 and 4. So it seems like if I look at the logical vector itself, which was temps less than 0, notice how the second element of this vector is true, and so is the fourth. So if I were to use which would tell me at which indices is this logical vector true. So pretty helpful now. But I'd argue that I'm not really asking the question I wanted to ask. Like I wanted to ask, is this piece of data an outlier? And an outlier can be both low or high. So here I've been focusing on outliers that are low, but I also want to find outliers that are high, like let's say greater than 60 degrees. So for that, I could use another logical expression, like temps greater than, let's say, 60. And if I run or evaluate this logical expression, what will I see? Well, I'll see false, 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 but I will see true for that 7th day, because that was a pretty high temperature there. So there has to be a way for me to combine, let's say, these logical expressions and ask the question I want to ask. And it turns out we can do so in R using what we'll call logical operators. Logical operators let us combine 2 or more logical expressions to ask a more complex question in code. Now, you might notice that I asked the question, is this value less than 0, or is it greater than 60? You often want to combine logical expressions with this idea of and, or. And in fact, R gives you a way to do just that. Here I have two symbols. One is the ampersand, and one is this vertical pipe. The ampersand represents and. I can combine two logical expressions and use an and between them with this ampersand. If I want to use or, for instance, I could use this bar here. This represents or for me. So for instance, let's say I wanted to ask the question, is this temperature below 0 or greater than 60? I would put those two logical expressions on either side of this vertical pipe, and the pipe would symbolize that if either of those expressions is true, then the entire thing is true. For and, by contrast, both expressions on either side have to be true for the entire expression now to be true. And you can think of this a bit like English. Something is only true if this and that are true as well. Now, unlike our comparison operators that we saw earlier, these logical operators actually work differently for vectors of logicals and single logical values. So these single symbols, ampersand and the vertical bar, those work for vectors of logicals. If you have a single logical value that you want to combine between, you need to use this double character set here, ampersand, ampersand, or vertical bar, vertical bar. These work for the single value, true or false, whereas these work for vectors of true or false. So let's try actually implementing now this in code to see if I can get at my question now. How can I find the outliers in this data set? Well, here I have my two logical expressions, and I want to combine them to represent one larger logical expression. Well, as I said before, I'm interested in whether a temperature is below 0 or if it's above 60, just like this. So this now is my full logical expression, and I can evaluate it or run it if I do Command-Enter on line 3. And now I'll see I've kind of combined my different expressions. I still see that these second and fourth values, this expression is true for those. They are less than 0. But I also see that on the element 7 here, that value is greater than 60, and so now that is true as well. If either of these expressions is true, less than 0 or greater than 60, I'll then see a true in this logical vector. And now I can go back to using which. I could use which to figure out at which indexes, which indices, these particular values are stored. So it seems like 2, 4, and 7. OK, so I think we're making some pretty good progress here. We've gone from using individual indices to now using entire logical vectors to automatically find for us at which places we have this condition being true. Some other functions to be aware of are these. One you might be curious about is this one called any. Any takes as input a logical vector and returns true if any of these values in that logical vector are true. So here I'm effectively asking not which values are outliers, but are any of them outliers? A yes or no question. And I'll get back in this case, yes, that some of these values are outliers. There are, in other words, some values true inside of this logical vector. I could also ask this question. Are all of these values outliers? Kind of a nonsensical question at this point, but you might use it in other cases. Are all of these values outliers? I can give this function, that same logical vector as input, run this, and I'll see false. No, not all of them are outliers. If any of them are false, I'll get back false. I need instead for all of the values in this logical vector to be true, for all to return true as well. All right. So one thing we might be wanting to do now is kind of tidy this up a bit. And so I could try to find those values in my temps vector by now using these logical expressions. And I could write as follows, temps bracket, and then in this case, let me go ahead and say which, and then let me type in the logical expression we decided on earlier. I'll say temps less than 0 or temps greater than 60. And now what will happen is, first, I'll evaluate this logical expression, finding all the values for which this expression is true. Which will convert that into some set of indices, at which point I'll pass those into temps. And now if I run line 3, I see my outliers without me going through the data myself. I could also decide to remove these values. If I decided to use a minus sign here, let's try this out, and I should see that same result, but now just dropping or removing those outliers altogether. But it turns out that which here is actually kind of redundant, that R allows me to do the following. I could actually index into my temps vector using nothing other than a logical vector. And what R will do is give me back all of the elements for which this logical expression evaluates to true. I think it's worth visualizing this, though. We're going to call this taking a subset of our logical vector, trying to find some elements for which a logical expression is true. And let's think of it a bit like this. Let's say I have my logical vector up top down here, or my temperature vector up top down here, and my logical vector down below here. I've called my temperature vector here temps, and my logical vector down here filter. Now, filter is a logical vector. It has these true or false values, and notice how they correspond to the indices in temps. So if I wanted to access only those outliers now, I could actually use this logical vector to index into temps and get the following. I can kind of index into it like this and mark some of these to be kept and some of these to be deleted. Now, if I complete this index here, I'll get back only those values for which the logical expression evaluated to true. So let's try this. I'll come back to RStudio here, and I will go over to my console, and why don't I try just running this line of code as it is. I know that this logical expression evaluates to a logical vector. If I wanted to, I can make this more explicit like we did on the slides. I could say my filter here, as if I'm trying to remove some values but keep others, is this evaluation here. And now, inside of temps, I can put filter just like this. And now, if I run line 3, inside of filter is this logical vector. I can then use this logical vector to subset, to access some elements of temps but not others, run line 4, and now I get back those particular outliers. OK. Now, what questions do we have on these logical vectors and using them in this case as a way to index into or take a subset of our vector here? All right, so seeing none, let's go ahead and keep going, and let's introduce one more thing here. So I promised that we would try to actually remove these outliers altogether. And one thing I've done so far is I've found the outliers and put them in their own separate vector. I haven't actually removed them. Now, one thing that's helpful when you work with these logical expressions is the idea of kind of inverting the result you've gotten. If I get a true value, maybe I actually want to get the opposite, like a false value. Here, I could do the following. Let's say I want to filter to only those temperatures that are actually not outliers. This logical expression here represents a element being an outlier. I could, though, negate this and say I want to find a value that actually is not an outlier by putting in front of this exclamation point here. This exclamation point means not. It takes a true value and converts it to false, or a false value and converts it to true. So let's try this. I'll run line 3. Just like this, and I'll update my logical vector. Now I'll run line 4, and I'll see that now I'm actually getting access to only those elements that are, in this case, not outliers. So again, this value, this exclamation point, this symbol, allows us to take a logical expression that evaluates to either true or false and negate it, get the opposite of that. In this case, true, or in this other case, false. All right. Let's see what else we can do. I'll come back to my RStudio over here. And one thing we also did is we kind of wrapped this logical expression, in this case in parentheses. This allows me to treat the entire thing as 1. Notice how I had 2 here, 1 temps less than 0 and 1 temps greater than 60. In this case, though, I wanted to negate the entire thing, so I wrapped that, in this case, in parentheses. And now I think we've kind of solved our problem. We've gone from, in this case, using these individual indexes to creating, in this case, a vector that excludes those outliers altogether. Now let's complete our analysis. I'll go ahead and try to save, at this point, a vector that doesn't include outliers. And I'll call it no outliers. So I'll go ahead and take my vector, temps, just like this, and I'll try to find, again, those values that were not outliers. I'll index into it using my logical vector, temps less than 0, or temps, in this case, greater than 60. And negating that, that means that this logical vector is taking the opposite now. And I could, if I wanted to, then find a vector of outliers, just like this, temps and then bracket, and then saying temps less than 0 or temps greater than 60, now not negated. And now I have two vectors, one that excludes the outliers and one that includes the outliers. And now, finally, if I wanted to save these vectors here, I could use this function called save that, similar to load, allows me to create an R data file instead of loading it into my environment here. If I type save, I can also then give save the actual vector I want to save to this R data file. I'll save, let's say, no outliers, and then the next argument is one called file. I could say file equals, and then say no underscore outliers dot R data. And if I run this line of code, line 6, I'll now have in my file explorer this data, R data file that says no outliers. I'm able to now save exactly this vector to my computer. And same thing now for outliers. I could save that one to a file called outliers.rdata as well. And I would argue this is our entire program, to open and load some vector, to find those outliers and to remove them, and now finally to save them to their own separate files. I could run this entire file with source up here and get all of these results saved to my computer. Now before we move on, what questions do we have on these logical vectors or on this saving and loading of R data files? Yeah, let's go to Mandeep.
I just want to know, do we have if statements in the R?
A good question.
And
So you might
how
have
do
heard,
we use them? Sorry.
yeah, good question. So you may have heard in other languages of these things called if statements that let you ask questions in other ways. We'll actually see those in a little bit as well. Let's take one more question here. Yeah, Vaishnavi?
So I wanted to ask, what kind of data files is the type R data? Is it like a CSV file or?
Yeah, a great question. So a difference between a CSV file and an R data file is that a CSV file, at the end of the day, is just plain text. You can open it and see the text you have in your data file separated by commas. An R data file, though, lets us save an actual R data structure, like a vector or a data frame, to a file and load it and put it back into our environment. So an R data file is not plain text, but it does allow us to save an actual vector of data, a data frame, and make it easy to load that data later on. So R data files are particular to R and its own data structures, a way of organizing data, like these vectors and data frames, unlike a CSV, which can be used across many different languages altogether. A good question. OK, so we've seen here how to remove unwanted pieces of data and how to do so using these things called logical expressions. Up next, we'll see how to take subsets of data and find those pieces of data we're actually interested in and ask questions of that piece of data instead. See you all in 5. Yep, testing 1, 2, 3. This is our data set of baby chicks and the kinds of food that they ate. Okay. Well, we're back, and so we previously saw how to remove unwanted pieces of data, like these outliers, using these things called logical expressions. Up next, we'll see how to apply those very same tools to now entire tables of data to find some subset of that data we're actually interested in. Now, to do that, we need to introduce this next data set, which is a data set involving these very cute baby chickens. And in particular, we have a table of data here, where each row represents an individual baby chick and how they grew up over 2 weeks of the very beginning of their lives. Here, notice how in every row represents a single chick, and every column has some piece of data about that chick. So here, line on column 1, this chick column represents a number for each chick, a way of identifying each chick uniquely. Now, this feed column tells us what kind of food that baby chick ate over the course of 2 weeks, and then this weight column tells us how much they weighed in grams at the end of the first 2 weeks of their life. Notice here how the feed column has food like casein, which is kind of like a protein, fava, which is like a fava bean if you're familiar, and then the weight column has their weight, in this case, in grams. So in this case, chick 1 seemed to have eaten casein and weighed 368 grams at the end of the first 2 weeks of their life. Now, one thing we'd be interested in is figuring out, well, what is the average weight of any given chick in this data set? We could certainly do that. We could look at all of the values in the weight column and average those and come to the conclusion that the average chick weighed, well, some amount, right? But I'd argue it's more interesting to find how much each chick weighed depending on what they ate. Like how much, for instance, did the chicks who ate casein weigh, and how much did the chicks who ate fava weigh? And what does that tell us about which food is more nutritious for these baby chicks? So let's see how we can use these same tools of logical expressions to now subset a data table like this and ultimately figure out these different averages across these individual different food groups. Let's come back to RStudio here. And what I'll do is I'll go ahead and maybe close temps.r, and I'll create for myself a new file. I'll do file.create in this case, and I'll call this one chicks.r. And I realized I didn't actually copy the file I need, so I'm going to need to do that and pick it up. Sorry. Yeah, I can do that if that works for you. OK. So I'm going to start from here. Cool. OK. Oh, waving at the screen? OK. Now let's come back to RStudio over here, and I'll aim to create now a program that can subset this data and find for me the average weight of these chicks based on the kinds of food they ate over time. So why don't I create a new file here? I'll do so using file.create, and I'll call this file chicks.r for these baby chicks that we're going to grow up and see how they do. So now I'll open my File Explorer, and I'll see I have this chicks.r file along with a new file called chicks.csv. So my data in this table is stored inside of this file called chicks.csv. why don't I go ahead and open this, and I can do so in the same way we saw last time, using this function called read.csv. So I'll type read.csv and the name of the file I want to open, in this case chicks.csv. And of course, read.csv will return to me a data frame, that is a table of data that is now represented in R's own format. I'll say that this data frame is called chicks, and if I run line 1, I'll now have that data frame stored in my environment pane. If I want to view this, I could use that same function we saw earlier, view, and I could then give chicks as input, and now I see I have my table of chicks and the various foods they ate. So true to the slides here, we have individual chicks, numbered to represent that individual particular chick. We have different kinds of feed or food the chicks were given. I see casein, fava, linseed, which is like flaxseed if you're familiar, meat meal, which involves various kinds of meat, soybean, the actual plant bean, and sunflower seeds. And here we have our weight column. Now I'll notice that unlike on the slides, like below fava here, I do seem to have some NA values, like the linseed value seems to be NA, same with this one here for chick 9, same for 11 and 12. Now these NAs could mean a variety of things. They might mean we didn't measure this chick, they might mean we measured it incorrectly and didn't want to include that data, but regardless, NA, as we learned last time, stands for not available. There could be some data point here, but there isn't. So we'll probably need to handle that as we go through and do this analysis here. Now I'll go back to my chicks.r file, and one thing I could do just off the bat is figure out how much do the chicks weigh on average across all different kinds of feed. If I wanted to find that out, I could use the mean function, as we saw just a little bit ago, and then give it as input the vector representing the weight column in chicks. And so here, all I'm doing again is accessing the weight column of chicks, which, as we learned last time, is a vector. Mean will take that vector and hopefully produce for me the average weight of these chicks. I'll run line 2, and I'll see NA. Well, let me go back to my data table again. I mean, I see NA values, but why do you think I would get an NA now if I try to find the average of the values in the weight column? Let me turn it over to our audience here. Why do you think I would get NA if I have NAs in the vector of weights I'm trying to find the average of? Let's go to Ahmed.
I think because it's grouping the other values.
Yeah, so it's kind of, you'd say corrupting other values in some way, or it's trying to maybe modify them in some way. Now, one thing in particular about these NA values is that they mean something special. There should be data here, but there isn't. And if you're doing statistics or data science, that's actually a really good indicator that you should make a deliberate choice about what you want to do about those values. You could remove them. You could substitute some new value for it, but what you shouldn't do is just ignore them and treat them like they don't even exist. And so R has a way of telling me now, look, you have NA values here. You need to make a decision of what you want to do in order to actually compute what you're trying to compute. So one thing I could do, which feels most natural, I think, for this case, is simply remove those NA values. And if I wanted to do that, I could actually use one of mean's other parameters, which I learned from documentation, called na.rm. So recall from last time, if I want this function to have more than one argument, I separate each with a comma. I'll say comma here, and then na.rm equals, it turns out from the documentation, na.rm is either going to be equal to true or false. na.rm stands for whether I should remove rm these na values before I compute the average. By default, na.rm is false. I won't remove them, but if I don't remove them, mean won't know how to handle them and so can't compute the mean. But if I were to remove them instead, that is to make this parameter, this argument, true, well, then I would be able to compute the average because I will have dropped or removed those NA values and then computed the average from the rest of those values that are in my weight column. So let me run line 2 here, now that the na.rm parameter is set to true, and I'll see that the average weight across all the chicks seems to be 280.6 0.77 grams or so. So a healthy weight for these chicks. Now, what I argued was more interesting was the idea of trying to find how much the chicks weighed depending on what they ate. And we could use that to figure out what is the healthiest kind of meal for these chicks. Well, one thing I might be interested in first is how much on average do the chicks who ate casein weigh? But for that, I'm going to need to only deal with the chicks who ate casein. So one way to do that would be to subset my data frame, only find the rows for which the feed column is equal to casein. Well, as we saw last time, there is a way to do this based on the indices of this particular data, of the rows here. Notice how on the left-hand side I have individual numbers for each of these rows. These are the indices of these rows. If I wanted row 1, well, I could use bracket notation and ask for row 1. If I wanted row 2, I could do the same thing. So I'll go back to my chicks.r code, and I'll try that as like a first step towards this. I'll say chicks as my data frame. And we saw last time that we can use a bracket notation to access individual values or elements of this data frame. Now, because a data frame is 2D, it took two values, one for the row and one for the column, two indices to represent the position of the row we want and the position of the column we want. Turns out that by convention, the row number comes first, followed by the column number, separated, of course, by this comma. So if I wanted the first row, I could do this, 1 here, that first row, and I want all the columns, so I'll leave this part blank. If I run line 3 now, what will I see? Well, I'll see just, in this case, row 1. Now, like our vectors that we saw earlier, these data frames can take more than just individual indices as input. They can also take a vector of indices. So let's try that. I'll give, in this case, chicks, a vector of indices that will then return to me all the rows for which the feed column equals casein. That seems to me, just based on eyeballing here, that it's these rows, 1, 2, and 3. So I could use the 1, 2, and 3 here, create a vector of those values, and then get back, in this case, all 3 of those rows. So now I have indexed into my data frame's rows, now using a vector, and I've gotten back all the rows that I care about. So why don't we call this one, at least for now, casein chicks. Why don't I actually try to save this particular smaller subset of my data frame in this object called casein chicks, and now if I wanted to find the mean or the average weight for those chicks, I could use mean, but then I could ask for the weight column from the casein chicks data frame, this subset of our previous data frame. So now I'll run line 4, and I'll see that the casein chicks seem to weigh significantly more than other chicks, 379 grams on average. Now, what might we want to use now that we've seen how inefficient this might be? Well, as we saw before, I often don't want to use individual indices. You could imagine me, the programmer, going through and trying to find, okay, well, 1 through 3 is casein, 4 through 6 is fava, 7 through 9 is linseed. That's not how I want to spend my time. There is a very minor improvement I could make to this, which is as follows. I could actually represent this same vector with the following syntax. I could use 1, 3. I've saved myself a few keystrokes, and I've gotten, in return, the very same vector. This colon here, when it's between two individual numbers, gives us a sequential vector, all numbers between 1 through 3 inclusive. And I can prove it to you in the console. If I ran this line of code down below, 1, 3, hit enter, I'll see I get a vector, 1 through 3 inclusive. Maybe I could do the same for, let's say, the chicks that are eating fava. Well, I could go 4 through 6 and get back those particular row indices, but at the end of the day, I'm still actually defining the indices at which this particular condition is true. I could rely on something better. I could probably rely on these logical expressions and use those instead. So what kind of logical expression could help us out here? Well, we might notice that we really care about those chicks for which the feed column is equal to casein. So I could try to make a logical expression that involves this feed column of chicks. Why don't I try that? I'll go back to chicks.r, and now I'll try this logical expression here. Chicks and the feed column therein when is that equal to casein? So recall that this is my logical expression. And because one part of it includes a vector, I'll get back a vector of logicals, of true or false values. Let me evaluate this expression by hitting Command-Enter. And now I'll see I get back this vector of true or false. And it seems to me, if I look at this vector over here, that these first three values in the feed column are equal to true. True, 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 are equal to casein, in fact. So true, true, and true, these are equal to casein. The rest, though, are not. They're false. Now, one thing to notice when you're working with data frames is that really these elements of this particular column called feed, these kind of correspond to the rows of the data frame. Like if I go back to my visualization of my data frame, I might notice that the first three values in the feed column, well, those correspond to the first three rows in my data frame. And similar to vectors, data frames can actually be subset with logical vectors. So let's see how that could work here. I have to keep in mind this relationship between the first elements of my column and the actual rows of my data frame, but I think we'll see how we could use these expressions to help us subset this data frame. Why don't we visualize it a bit like this, where before we had seen that we had a data frame called chicks, and we could access it using bracket notation, entering in the indices for the rows or for the columns. But if I had some separate logical vector, like the one I just created, and I called it, let's say, filter, just for simplicity, I might notice that all of those same trues and falses, the way they align now with the rows of my data frame. So here, for instance, this logical vector was created by comparing the values of feed with casein. Those first three values were in fact equal to casein, but the kind of revelation here is that these same elements now correspond to rows of my data frame. I could take this very same logical vector and put it into the place where I would actually ask for the different rows of my data frame, and I would get back the following, something like this. I would mark, so to speak, certain rows to be kept at the end of this execution here, and certain rows to be removed, and I would ultimately end up with only those rows for which the logical vector evaluated to true. I would have, in fact, a subset of my data without touching any of the actual individual indices. So let's try it in R. I'll come back to RStudio here, and I will do as follows. I will try to prevent myself from using these individual indices, and I will instead use this logical expression. Similar to the slides, why don't I just call this logical vector filter, just like this. And why don't I run line 3. Now I have, in the case of filter, what do I have? I have a logical vector. Now I could use this logical vector to index into, to find a subset of my actual data frame here, if I use it instead of some individual indices to index into this data frame. Now if I run line 5, I'll have subset my data frame. And if I run line 6 now, I'll see exactly the same result. And I can even show you what casein chicks looks like. Let me show you in the console here. I'll see I in fact have the chicks that ate, in this case, casein. I could change this filter though. Let's say I want the chicks to eat something like linseed. I could use linseed here. And now let me rename casein chicks to linseed chicks and find out how much they weighed, those chicks who ate linseed. I'll rerun my code top to bottom. On line 3, I'll change my filter. I'll get back a logical expression representing those elements of feed that were equal to linseed. And then on line 5, I'll go ahead and subset my data frame again. And now I'll have only those chicks who ate linseed. And now could I find the mean if I run line 6? And so it seems like the NAs are still involved here. I need to now do the na.rm here, equal to true. I want to remove the NA values, and I could find on average how much those chicks who ate linseed weighed. Seems like it was 229 grams, that is. So let's pause here and ask what questions we have on using these logical vectors to subset these data frames. What questions do we have? Let's go to Ahmed.
Sir, I have two questions, but I don't know if it's in a coming lectures or no. Can I discuss it?
Sure, go ahead.
Okay, the first question, are we going to use functions or yes, functions or recursion in our programming language?
Yep, so familiar with this idea of recursion. It's the idea that a function can call itself when it runs. R does support the idea of recursion, which we might see a little later on potentially. We'll see.
Okay. Second question, can I import a function or a filter input from another R file to use it in this file or no?
Yeah, so a question here, we've been creating this object we've called filter so far. In reality, though, you could have any logical vector and use that as the vector you use to subset your data frame or your vector. You could call it anything you want, and you could take that logical vector from anywhere. As long as it's a vector of true or false values, you can use it to subset your data frames or your vectors. Other questions then on these logical vectors or these data frames and how to subset them? Let's go to Valentino.
Okay, sir, thank you very much for that. I have some problem if I have some another some file like Excel or such file. Can I make to the test or not? Thank you very much.
Yeah, so I can't quite hear you, unfortunately. And if you have some trouble with like actual bugs in your code, I encourage you to reach out online. But I'm sorry I can't answer that one, at least right now, without seeing code more in depth. Thanks for asking, though. OK, so let's keep going. And let's go ahead and think through how we could write some more improvements to this program. Now, as I just saw, like I don't want to have to write na.rm equals true every time I encounter these na values. What I would love to do instead is actually just filter out these na values to begin with. Maybe load my data set, but then as soon as I do, remove all the rows that have an na value for the weight column. So for that, I could probably still use a logical expression, and one that comes to mind might be something like as follows. Let's say I want to figure out first which elements of the weight column, or really which rows in my data frame, are equal to na. Or let's say maybe not equal to. So I'll do chicks here, and I'll find the weight column of chicks, and I'll ask the question, which ones, in this case, are equal to na? So I can maybe remove them later on. And you might notice that I get this little yellow squiggly sign in R and this little warning that says use is.na to check whether the expression evaluates to na. I'm going to ignore that for now. I'm just going to run line 3 here and see what we get. I'll see I get a vector of na values. And this has to do with the fact that R really wants you to know that na values exist. If you have an na value in your logical expression, it's going to make everything else na, because R wants you to decide what are you going to do with this na value. So it seems like this approach won't work, but thankfully R does have other functions that we can use to be more deliberate about checking for na values in some given vector or in some given data frame. Now in R, these are known as logical functions, functions that can return to us a logical value, and there are a lot of logical functions that are based on these special values we saw in R last time. You could imagine the is.infinite function. We saw last time there was a special value called infinite, or inf, that allowed us to represent a very, very large number. You could use is.infinite to test if some value is infinite. You could also use, as we just saw, is.na. Is.na looks at some given value and returns true if that value literally is na. If it's not, it returns false. Same for is.nan, or is.not a number. Remember that special value called nan? Well, this tests for that value. And same for null, that special value called null we saw last time. That will return true if we have the null value, or false if we don't. But I think the one we're going to care about here is is.na. So let's try that one out. I'll come back to my code over here, and why don't I try to use is.na on this weight column in chicks. I can pass as input to is.na this particular vector. this column called weight. And now if I run line 3, well, I'll get back a vector of logicals, a logical vector, and I should actually see which, in this case, elements of the weight column are equal to NA. So it seems like, I mean, I might want to use which here, but it seems like 1, 2, 3, 4, 5, 6, 7. The 7th value seems to be NA. Maybe the later one too. Let's actually use which for this. I'll come back to RStudio, and why don't I use which? Let's say which values, which elements of the weight column are equal to NA, and I'll see that it is, in fact, seems to be the 7th, 9th, 11th, and 18th, 12th and 18th rows in chicks. Now, that seems helpful, but I would ideally like to find those values that aren't equal to NA and keep those instead. So if I wanted to negate this expression here, as we saw before, I could use the exclamation point, this not operator that says, if you gave me a false, give me instead a true. If you gave me a true, give me instead a false. So this will test which values are now not NA in that weight column. I'll run line 3, and now we'll see we have more trues than falses representing all those values in our weight column that are not, in this case, NA. So if I wanted to subset this data frame, I could use the same kind of trick we saw earlier of realizing that these individual elements of this vector correspond to the rows of my data frame. And I could subset, in this case, chicks as follows. I'd say chicks and give it this logical expression, which in fact returns to me a logical vector, and then use that logical vector to subset the chicks data frame to now only include those rows that in this case have a weight that is not equal to NA. Now, it would be good for me to maybe save this as the most recent version of chicks. Now, on lines 1 and 2, I'm loading the chicks data frame, and I'm now saying immediately I'm going to remove any NA values in the weight column just like this. So now, when I use mean later on, I won't need to use na.rm because I'll know that all those NA values in the weight column are gone for good. Now, there is one more way to subset these data frames as opposed to using this logical expression that is kind of serving as like an index into this data frame. There is actually a function called subset that works on data frames and takes both a data frame and a logical vector as input, returning for us all the rows for which that logical expression is true, that logical vector evaluates to true. So let's try this. Why don't I instead use subset here? I want to subset my data frame to only find those rows where weight is not equal to NA. Well, I could still use subset. I could use subset here, which means the subset function, and I could pass as the first input to subset the chicks data frame. And now as the second input, the second argument, I now need to give it a logical expression to evaluate, to see which rows to keep and which rows to exclude. Now, one thing is I could say is not is.na. So this means any row that is not equal to NA, and I could then give the weight column of chicks as input. Notice here the syntax is a little bit different. I no longer need to use the $sign notation to actually access the row, the column of chicks. I instead just type in the column itself. And this works because subset takes as input the data frame. It will assume if I say weight, I'm talking about, in this case, the column in chicks. So this should have the same result. If I run line 1 and then line 2, if I view now chicks, I should see that all of those weights that were previously NA are gone from my data set. I could even use this, let's say, later on to figure out how much on average the chicks who ate, let's say, soybean weigh. Why don't I use subset again? I'll make an object called soybean chicks, just like this, and I will then subset the chicks data frame, the latest version of it, and I'll try to make sure that, in this case, the feed column equals, what do we say? Soybean equals soybean. Again, because I'm now using the subset function, I don't need to tell R that the feed column belongs to chicks. Subset will do that work for me. I can just give the column name and ask, where is it equal to soybean? And now subset will return to me all the rows in chicks where this expression is true. Let me run line 4 then, and let's see what's inside of soybean chicks. We'll see that now I have that subset of my data frame. And I could now run analyses like mean to determine how much on average did those particular chicks weigh. All right. Now, one more thing to keep in mind is that if I were to view this chicks data frame just like this, if I'm being very astute, I might notice something a little bit off about it. So I have the individual numbers representing each chick here, but data frames in R also have what's called row names, individual indices for our rows. And if I wanted to find those row names, I could use this, row names, as a function. And I could run row names on line 4, and these are the row names of this data frame. Now, if you're being a little observant, what do you notice? Now that we've run line 2, what might be missing from these indices of our data frame? 1, 2, 3, 4, 5. What are we missing in the end? Let's go to Ahmed.
I think it's the NA or not available variables.
Yeah, so we're missing, in this case, all of those row names that previously corresponded to those rows that had an NA value in the weight column. So we have 1, 2, 3, 4, 5, 6, oh, and where's 7? Well, 7 we saw earlier actually had an NA value in the weight column, so we removed it. But it's really not good practice for me to actually have these row names not now ascend one after the other in sequential order, to have these missing values here. So I need to reset them. And I can do that using a special value that we saw earlier called null. I'll come back to RStudio here. And if I want to reset the row names for this chicks data set, I could do as follows. I could not just print row names or see what they are. I could assign them some value. And R has a handy trick where if I assign the row names of some data frame to be null, capital N-U-L-L, that will reset them to count sequentially, 1 up through the number of rows we have. Now null, remember, meant literally nothing. There's intentionally no value at all here. It means nothing at all. But when I assign this value to be the data frame's row names, it kind of gets rid of them, and R decides to build them back in. So let's try this. I'll run line 4, and now I'll check on the row names again, and I'll see that we're back to now being in sequential order. So whenever you take a subset of your data, consider updating the row names to make sure that things are staying just as they should, and you have the actual row names in ascending order to index your data, in this case, properly. Now, what final questions do we have on subsetting these data frames? What questions do we have? Let's go to Bruno.
So when you introduce the isNA function for in conjunction with the which function, we had the indices that had NA on them on the weights vector. Would we have an easy way to count how many NAs we had in the vector? Because maybe if we had a bigger data frame, we would have like a hard time counting the number of indices that it returned. So this is the question.
No, a really good question, Bruno. And so one thing you'd be asking yourself is, how do I figure out exactly how many NAs I had in the first place? Well, we can use a little handy trick of these logical values, the true or false values, which is that at the end of the day, a true corresponds to a 1, and a false corresponds to a 0. So let's actually see this in action, see how we can actually count up our number of these true or false values. I'll come back to RStudio here. And our question was, how many NA values did we have in the weight column of chicks? Well, we used, remember, is.NA to test and see which elements of the weight column were equal to NA. If I use is.NA here, I get back this logical vector. And actually, right now, all of them are false, because I actually am still working with the updated version of chicks that removed those NA values. Let me run line 1, which will reload the CSV. And now let me run line 3, which now has those NA values added back in. Now I'll see that some of these values are true. That is, there are some places in the weight column of chicks that are equal to NA. Now, a useful trick when you're trying to count up these kinds of values is to keep in mind that true underneath the hood corresponds to the number 1, and false underneath the hood corresponds to the number 0. And I think if I were to do this, if I were to do in the R console as.integer, this value true, this would take the value true and show me its true integer representation. Let me run enter here. I see 1. Let me do as.integer for false to see what it really is underneath the hood. That seems like it's a 0. So I could take this vector of trues and falses, and I could sum it, just like this, where sum will allow me to count up all the possible values in here. And because true is always equal to 1 and false is always equal to 0, what I'll really get back is the number of trues that are inside this vector, or the number of values in the weight column of chicks that were equal to NA. So I'll run line 3, and I'll see that there were 5 values in chicks that were equal to NA. If I view chicks now, I think we should see, if we count for ourselves, 1, 2, 3, 4, and then down below, 5, exactly 5 values of NA. So you can keep in mind this when you're trying to count up your number of NA values that you might have. Okay, we'll take a quick break here and come back to talk more about how we can not just choose the subset of data ourselves as programmers, but give the user more control over choosing which subset of data they want to see. We'll be back in 5. Well, we're back, and so we've seen so far how to subset vectors and data frames, but up until now it's always been us, the programmer, deciding which subset we wanted to see. Now in this segment, we'll take a look at how we can turn more control over to the user and let them decide which subset of data they want to see from our larger data set. Now a common method of taking user input in R is to present a menu to the user, maybe a menu of options they could actually take a look at. Here's one such menu for our data set here. We can maybe prompt the user like this and say, enter the feed type you want to view. If they want to see all the chicks who ate casein, they could type a 1. All the chicks who ate fava, they could type a 2, and 3, and 4, and 5, and 6, and so on. And once they do so, we'll present them then with the appropriate subset of this data frame. Now, there will be some work to do here to present the user with these options, but once we get through that, we can then see how to provide the user with that subset of data they asked for and handle the various cases the user might give us as they enter in this data into our program. So let's focus first on creating this menu and showing it to the user. I'll come back to RStudio here. And why don't we create a new program, this one called feed.r, because the user will then choose which feed they want to see. I'll type file.create feed.r, and similar to in the past, I'll go to my File Explorer and open up feed.r. And now the first thing I probably want to do in this particular program is read in that same data file from before. I will, in this case, read.csv. I'll read that same chicks.csv and store it in now an object called chicks, a data frame to be more precise. Now, I'll do the same thing we just did. I want to remove those NA values from this data frame, which I can do by subsetting my data frame. I'll reassign the object chicks to instead be the subset of chicks in which this logical expression is true, that the weight column is not NA. That will remove for us any rows in which the weight column is NA. So this, let's say, is the part of our program where we read and clean the data. So I left myself a comment here, noted by this hashtag, to say this is the segment that reads and cleans the data that we have. Now, if I want to present the menu to the user, one of the first things I should do is figure out what options I could even show them. So let's try that. I want to determine, in this case, the feed options. And one thing we could use is the function we saw a little bit last time called unique. Unique looks at a vector, like let's say the feed column in chicks, and then tells us what kinds of options, what unique categories of data there are. So I'll type unique, and then I'll give as input the feed column of chicks. And if I run this line, I'll see I now get back all of the unique values of feed I could use. Why don't I just store this in an object called feed options for now, and I can use this later on in my program. So let me go ahead and run this line of code again to store it now in feed options. And let's now think about how to print this option out to the user. Well, I'll call this part called prompting the user with their options. And now I could think, how do I best show the user these options that are inside of this feed options vector? Well, we saw last time we had this function called print, and print is great for printing out data to the user. I also want to introduce you, though, to this other function called cat, where cat can both concatenate various character strings, as we saw last time, and immediately print them out to the user, which might be what we want to actually do in this case. So let's try printing out the first option for the user. Well, if you recall, we wanted to kind of prefix a number to that option, like 1 for the first option, 2 for the second option. So let's try just the first option. I'll use cat here, and cat takes in multiple arguments. The first argument might be the very first character string I want to print to the user and concatenate with some other character strings. So to go with the flow here, to go with our theme, I could say 1 period, and then maybe a space afterwards. And then I'll follow it with a comma, because now I want to combine some other character string. I want to combine, in this case, the first option that the user could see. So I'll look at the feed options vector like this, and I'll choose the first element. Now if I were to cat this to the user to print it out on the console, I could run line 9, and I'll see 1 dot, and then space casein. So it seems like cat has that same idea of actually inserting a space for us automatically between these character strings. I could, of course, remove my own space and allow cat to handle that part for me here. So now I see one period space followed by casein. So I think we're on the right track. One thing I could do is kind of just copy and paste. I could copy this line here, and so I could then do this to show all the options to the user. First the first, then the second, then the third, then the fourth, and then the fifth here, and then the sixth, and so on. Let me just change these numbers, 5, 6, and 6. And now, once I've shown those to the user down in the console, I could try to get the actual feed choice they want. So why don't I ask them to input some data? I'll say feed type to say enter this number of the feed type you want to view. Why don't I then immediately convert that to an integer, as we saw last time, and why don't I store this in an object called feed choice? Whew. So this is, let's see, 7 lines of code to prompt the user with this menu, and then to ask them to input some number to see what it is they want to see. Now let's run this code top to bottom, and again, to do so, I can use source up top. I'll make my console a little bigger so you can see what's happening, and I'll run source. And now I see something a little odd. So I do see the options. Like I think I'm in a right place here. But I also see that they're all on the same line. And that's probably not what I want for the user to see. So I'll need something else to help me here. This thing that can help me is known as an escape character. There's a special character that actually denotes a new line that says move this cursor to a new line and start printing from there. Let's take a look at what those characters could look like in general. So we have in R this idea, and other languages too, this idea of escape characters. These characters mean something special, and we actually print them out to the console. One of them is \n, which stands for a new line. We won't actually see this character, \n, printed to the screen, but we will see a new line, hitting return effectively on the output to move our text to that next new line. Same thing for \t, but this one stands for a tab character. When you press tab on your keyboard, if you wanted to actually have that tab in the output to the user, you could use \t, and you wouldn't see \t, you would instead see that tab character. So in general, these escape characters are characters that look one way when you type them, but mean something special, and they transform into something else when you actually show them to the user. So I think I could fix this using \n to show the user now this full menu. I'll come back to my code, and let's try this. So instead of, let's say, printing out every option, as we're doing here, on the same line, why don't I actually incorporate now a \n at the end of every line? And that should hopefully now move the input after every call to the cat function down now one new line. So here, I'll print the first option. And at the end of that line, I'll move the cursor to the next line, effectively hitting enter. And the same thing for the second, and the same thing for the third. Well, let's try this again. I'll pull up my console. And if I want to just quit my program, I don't want to enter anything, I can use Control-C. Control-C says exit this program that's currently running. I'll use Control-L to clear the console. And now if I run source, well, now I think we're more in business. I do see that I have all these options: casein, fava, linseed, meat meal, soybean, and sunflower, now each on their own new line. All right. What questions do we have about these escape characters, or about cat, or about anything we've seen so far in this program? All right. Let's go to Ahmed.
Okay, first, as we concluded from the first 2 lectures, I think programming with R is not safe enough because it saves arguments or variables. Then after it, you can't change it, or you can't access the first element. So how we can program defensively with these available features?
Yeah, a good question, and I like the way you're thinking. Like, we need to think of how we can program defensively. And so one way to think defensively here is to think through what possible input the user could give us. If I look at this particular prompt, I offer the user that they could type in 1 through 6 here, but what if they typed in like a 0 or a 7? Like, they could very well do that. And so we'll see how we can actually handle those kinds of cases in a little bit. But first, I would argue that this, although it works, isn't exactly the best designed program we could write. I do have the right kind of menu for the user to see, but I could probably improve the design of my code too. So let's come back to RStudio and think through how we could improve the design of this code using R's vectorized features. So here, if you notice on line 9 through 14, like, there's no reason for me to type all these lines of code. And if you find yourself ever accessing one element of a vector after another just to print something out to the screen, you could probably think to yourself, there has to be a better way to do this. And in fact, there is. One thing that you might often think about is transforming your output to the user and turning it into a vector itself. So here I have all of my formatted options in terms of individual lines of code. But it would be really, really nice if I had a vector of these formatted options, and I could then pass that vector to cat, for instance. Now, cat can take a full vector as input and separate those separate those elements with some character I tell it to. Now, for instance, I could, if I had this vector called, let's say, why don't we call it formatted options, and that is a vector itself, I could pass that vector to cat and tell it, in this case, to separate every element with a \n. And so long as this vector of formatted options included 1 for casein, 2 for linseed, and so on, it would then be able to print all of them out at once, separated by a new line. Exactly what we just did, but now using only one line of code. Now the challenge is, though, how do I get these formatted options in terms of their own vector, and how can I pass them, in this case, to cat? Well, I think we need another part of our program now. I'll say, let's make a section to format our options, and to do so a little better than we did before. So I claim that ideally we want to create an object called formatted options that looks a bit like this. This object is a vector, and it includes, for the user, all of their menu options. So this is 6 total options, each one here, 1 for casein, 2 for fava, 3 for linseed, and notice how I've kind of appended these numbers in each case. 1 dot space, the food option, 2 dot space, the food option, 3 dot space, and the food option. Now I'm kind of noticing a pattern in this vector here, which is that for the most part, every option I have begins with a number, 1 to 6 down here. Then we have a period followed by a space in every element of this vector. And then the next thing I see is we have whatever food option corresponds to this particular option, like casein, fava, linseed, or meat meal. Now, when you're using R and you're using vectors, it really pays to think in a vectorized way. So I could actually think about this single vector as the combination of 3 different ones, these right here. Maybe I have one vector of numbers, 1 through 6, one vector of just that dot space, which I've quoted here to show the space, in fact, one vector of just those dot spaces, and one vector, which we already have, of those feed options to show to the user. And it would be really nice if I had a function to basically combine these various vectors into a single one, to take these 3 and concatenate them into one single list of formatted options. Now, you actually already know what that vector is. In fact, that vector, not that vector, that function, you know what that function is? That function is paste, and its sibling paste 0. Paste can still work with these vectors, but concatenate them now element-wise. So let's try using paste to vectorize our formatting here and improve the design of this code in R. I'll come back to RStudio here. And again, our goal is to create this vector called formatted options that has the number prefixed to each of our options to show to the user. Now, if I wanted to do that, I claimed we could use paste 0, but instead of giving paste 0 several individual options, I could give it a few different vectors. So maybe the first vector to give to it is the number vector. I want to first begin my input with those numbers, and so I could do as follows. I could say 1:6. That represents the number of the vector, the number vector that I have. If I go down to the console here, I can prove to you that 1:6, that is in fact a vector of 1 through 6. Okay? Now the next part was to incorporate that dot space in the middle. And I claim, before I show you this, that I can actually get away with not putting this in its own vector, but instead putting it as a single value, and R will repeat that value for me, or recycle it for me, as we'll see. Then the third input in this case is the actual option that the user should see in terms of the feed options. So I'll type feed options here, which, as we saw, if I go down our console here, is just a vector of the options we want to show the user. And so visually, what we've done here looks a bit as follows. It looks like these three inputs to paste, and paste 0 in particular. I have my vector, 1 through 6, my single value, period space, and then my vector of the feed options to show to the user. Now paste 0, I claimed, would concatenate these different values element-wise. So let's see what that could look like here. We'll get back a vector of options because we've given paste 0 vectors as input. And this first one seems pretty obvious. We'll combine 1 with the dot space with casein and get back now 1 dot space casein. So that's a formatted option that we have. But now, if I look at the second option, well, I don't see something to use as the middle part of this concatenation. This dot space doesn't seem to repeat itself. Well, no worries. R will actually do what's called recycling this value. It will recycle it downwards and let me actually reuse it throughout each of these element-wise concatenations. I'll do 2 dot space fava and get fava. I'll do 3 dot space linseed and get linseed. I'll do 4 and 5 and 6 and so on to get, in this case, the entire vector's output on the right-hand side. So let's see if this worked. I'll come back to RStudio here, and let me try to see what's inside of formatted options. Let me go over here, and let me first run, let's say, line 9. Let me now see what's inside of formatted options. And here we actually see our formatted vector of options to print to the user. Now, what questions do we have, if any, on how paste has now handled these vectors as input? Let's go to Bruno.
Could we make our concatenation a little bit more flexible, maybe using the length of our feed options vector? Because maybe if we added another chicks that ate additional foods, maybe we could make it a little bit more adaptable. So that is my question.
Yeah, I love the way you're thinking, which is maybe we, at some point, will have more than 6 feed options. Maybe we'll have 7 or more. And we want to write a program that can be flexible in those cases. And you can, in fact, do that here in R using just what you said, this length function. So we'll take a look at that and how we can make our program more flexible, too. There is a function called length in R that tells me how long a vector is, or really how many elements are inside of it. If I go to format options here, why don't I try to first find the length of my options? Why don't I say, make an object called num options, just like this, for number of options I have. I could make that the length of feed options here. And now if I run this line of code, I'll see in my console that num options is equal to the number of options I have, which is 6. And now, I think the part where it could be more flexible is on line 10. Instead of 1:6, which kind of hard codes that value 6, I could instead do 1:num options, just like that. And that would then let me create a vector. In this case, let's try it out, 1:num options, 1 through 6, at least right now. But if num options was 7, I would then have 1 through 7. If num options was 8, I would then have 1 through 8. I could still do this as follows. I could actually remove this extra object called num options, and I could just do the following. I could say 1 through the length of feed options, which I think sounds a little better to me if I'm reading this left to right. Let's create a formatted options vector that first includes a vector of numbers, 1 through the length of the options, 1 through the number of options we have, followed by a dot space, followed by the actual feed options to show to the user. A really good improvement to make here. So let's keep going, and let's actually try this out in our console here. I will now source this file, and hopefully we'll see the same exact result to show to the user. So we've really improved the design now, taking advantage of R's vectors. Now, one thing that we touched on a little earlier is we wanted to try to really show the user the feed options that they typed in, but we also want to take into account the user being kind of malicious, entering in some value we didn't expect. And so let's tackle those two ideas now in turn. Well, I argue that we now have a way to show a menu to the user, and feed choice gives us that number of the food option they selected. It's now up to us, our program, to show the user what kind of subset they should be seeing. So what I should probably first do is think about how I could convert the number the user entered into the actual text, the feed option, like casein or linseed, and use that to subset our data like we just did a little bit before. One way to do that would be to index into the feed options vector using the number the user gave us. Because recall that if they give us a 1, that means they chose the first option in the feed options. If they gave us a 2, that means they chose the second option in our feed options. So I could very well just do this and get back, let's say the user entered a 1, I would get back, in this case, casein. If I entered a 2, down below here, I would get back fava. I could then maybe name this as a separate object down below, and let's call this the selected feed. That is the text-based representation of the feed they chose, and now I could print the subset of chicks where the feed column is equal to the user's selected feed, just like we saw a little bit before. Let's now run this code again. I'll run it from top to bottom now using source, and if I choose, let's say, 1, well, I'll see the casein chicks. If I run this code again, let me do source, let me do 2, I'll see the fava chicks. If I run source again and see type 3, well, now I see all the chicks who had linseed and whose weight wasn't equal to Na. So this is pretty nice. But what if, as someone suggested earlier, what if the user types something in like this, 0? So this, it seems, is not the output I want them to see. Let's try something else. Why don't I do source? Why don't I do 8, which is certainly outside of our valid range? So we're still printing something to the user, but I don't want to do that. It seems to me like I should really only be running these lines of code to print, in this case, to print the selected option, if the user enters some valid actual input. Now, this idea of only running some lines of code if some condition is true is actually fundamental to programming, and we can use this kind of idea if we think and learn about these things called conditionals, where conditionals allow us to specify some parts of our program that only run if some condition, some logical expression, is true. Now, to make a conditional in our code, we can use this keyword called if. And if is then followed by a logical expression inside parentheses. And if that expression is true, we'll do the code that is inside of the braces, at least in R, inside of this particular language. So let's see if we can actually guard against these different kinds of input the user could give us now using these conditionals. I'll come back to my R code, and let's think about the condition in which we actually shouldn't show the user anything. Maybe we show them something like invalid choice instead. Well, if I want to make this if statement, this conditional here, I would first type this keyword if, and then I would follow it with, according to R's syntax, some parentheses, open and closed. And now it's inside these parentheses that I can put my logical expression. Now, a question for you to think about is, in what case would the user's input be invalid? Well, it would be outside of the range of 1 through 6. It's either less than 1, let's say, or greater than 6. So I could check if the user's feed choice, that is the object storing their number they entered, 1, 2, 3, and so on, if the feed choice is less than 1, or, let's say, or the feed choice is greater than 6, well, in that case, we want to do the following. We want to print or cat to the user that, in this case, they made an invalid choice. And notice how at the end of this if statement, I included this open brace and this closed brace, and now only the code that is inside of those braces will be run. I have also stylistically indented this code 2 spaces, 1, 2, just like this, and that tells me that this line of code will only run if this logical expression now is true. Okay, one more thing to notice before we go on is that this double pipe here, these double bars, this is now being used on 2 single logical values. We saw earlier the single bar for working with multiple vectors of logical values. In this case, though, we have 2 single logical values. Feed choice is less than 1 or it isn't. It's only 1 true or false value. Feed choice is greater than 6 or it isn't, but it's only 1 true or false value. We can combine them now using OR and ask this question, is the feed choice an invalid choice? Okay, let's go ahead and run this line of code, or run this program. I'll click source now and try to enter something invalid. I'll say, let's go for 0 again, hit enter. Oh, and now we're getting somewhere, but I still see this. I see invalid choice, so it seems like that code was run, but I do still see now the output that I don't want the user to see, which is R trying to find the feed option that corresponds to 0, but I mean, it can't do that, it doesn't exist, right? So we'll still need another tool in our toolkit to actually avoid running the code that's below the if statement. Let me come back and show you what I mean. If we come back to our program here, notice how no matter what happens in this conditional, whether the feed choice is invalid or it's not, our program will still run top to bottom. It will go past line 17, and it will then try to print the selected option. But at least in this case, if this line of code executes, well, what I don't want to have happen is this line of code. I want to make these exclusive. Either you should print invalid choice, or you show the user the subset they asked for. Now to do that, we'll introduce these other keywords, one called else if, and one called else. These allow us to specify blocks of code to run in the case that the previous conditional was not true. So let's go back here. Here, let's assume the user actually enters well, let's assume they enter a valid choice, in which case I think our program would still work. But really, I think the problem now is if they enter an invalid choice, if they enter something less than 1 or greater than 6, what I don't want to do is run this code below. So I could guard against that. I could make sure that only this code is run if this condition is true by putting this code inside of what we'll call this else block of code, else, just like this. Why don't I move now these lines of code up into this else block, and remove my comment here, and now my logic is as follows. If the feed choice is invalid, I will print, or cat to the user, invalid choice. Else, though, I will show them the feed option they asked for. And now notice if they enter an invalid choice, I will print invalid choice. But if they don't, if they enter, or if they do enter invalid choice, they will print invalid choice. But then I won't run this code that's now inside the else block here. They won't see the subset of data that I'm trying to print down below. One thing I could do is ask another question too if I wanted to. Let's say this if was not true. I could also ask another question. I could say else if maybe the feed choice is valid. I could say if the feed choice is greater than or equal to 1, and let's say it's less than or equal to 6 in this case, well, I could then print out the subset. But let's think about this. I could either use else or I could use else if, and I'm curious which you think is more efficient, else or else if in this case. If you were the programmer, how would you decide which to use? Let's go to Mandeep.
I will use else because I'm already checking the condition in if, so there is no point of using else if. But if there would anything else I have to do, then I will just else if. But for now, it's else.
Yeah, if we think through this a bit logically, our first question is the input invalid? And if it's not, we would then ask the question, is it valid? but it kind of logically goes that if the input isn't invalid, well, it has to be valid. So there's no use asking that second question here. So I'd argue there's no need for this else if. There are, though, scenarios where you could want to use an else if, namely if you want to ask one question after another. But in this case, else, I think, will work just fine for us. This part of our program will now be called printing the selected option. But of course, if the user enters an invalid choice, we'll tell them and not do anything else. Our program will instead just end. So let's try this. I'll source this file. I'll now type 0, and I'll see invalid choice and only invalid choice. That block of code inside the else is no longer being run because that condition was true. Let's now run it again. I'll do 1, and I'll see the right option for the user here. I'd argue, I think, our program is working pretty well. Now, we can clean this up a little bit. We've actually been implementing something that R already has as a bit of a feature for itself, and that is the idea of a menu. So I said before that R has a way to get user input using this idea of a menu. We recreated that ourselves using, in this case, paste 0 and cat and so on. But we could simplify our lives a lot if we just used R's menu function. So let's show you that. Up here, I want to maybe think about how I could re-implement these lines of code now using this function called menu. I'll call this part of my program just prompting the user for input, and I'll now use the menu function, where the menu function's first argument in this case is the feed options to show the user. That is a vector of options to show to the user. I don't have to number them, do anything else. Menu will take care of that for me. Another argument, another parameter to menu is called title, where title is, in this case, the question I want to ask to the user. Before we had feed type colon, so I'll keep that the same here. And now menu's return value is the number the user selected, whether 1 through 6 in our case. So I'll use feed options here and use the assignment operator to say, oops, sorry, not feed options, I'll use feed choice and assign the return value of menu to that object, representing now the user's choice. So I think that we've replaced a lot of lines of code now with these here. Let me try running this code so you can see the differences now. Let me source this file, and now I'll see R's own menu. It looks a bit like R's with some minor variations. It seems the question is now up top. We say feed type. The user could enter in 1 through 6, and now we see this selection kind of text down here with a blinking arrow. The user could now type 1 through 6, or if they typed something like this, if they typed something like 7 and hit enter, they would be reprompted. I could type 8 and be reprompted again. I'm going to be prompted until I actually comply and I provide a 1, and I want to see the options that I can see. So this is the use of the menu function in R. What questions do we have on menu or on anything we've seen so far with this program? Let's go to Luis.
Will our vector of unique selections always match up to what is being displayed with the menu so that the user has this correspondence between indices?
Yeah, good question. And that is the case with menu. So when we provide a vector to menu, it will then automatically number those options for us, treating it as the first element in that vector gets number 1, second gets number 2, and so on. So it does maintain that kind of relationship between the vector options and the numbers therein. Good question. And Ahmed.
Okay, can we use raise value and for and try and accept, and we will raise a value error if we got it?
Good question. So if you're familiar with programming, you might have heard of these things called loops, like for loops. And it seems to me like there is some kind of loop going on in this program, like we're being prompted again and again and again for something. We'll actually see more of those in the following lecture, but for now we'll leave it just at this. But a good question. All right, one more design improvement here, actually. To our earlier point, what if our program expands beyond just 6 options? Well, it seems to me like I should be able to handle that case and make this program even more flexible. Well, on line 15 here, why don't I actually remove this 6 here, which kind of hard codes the number of options to be 6. I could instead make this as follows. The length, in this case, is going to be, let's get the length of the feed options. The feed options vector. So this will then make it so that if my feed options vector changes, let's say it has 7 options later, I can then actually check for an invalid choice from the user there. Let me go ahead and source this file again, and I'll type in, let's say 5. I'll still see soybean. Let me go ahead and source again. I'll still see 7 and 8, and it seems like it's still working. One thing, though, to keep in mind is that I think we still have this code that belongs to a prior version of our program, where down below we're checking if the actual choice was invalid. What's nice about menu is that we don't even need that anymore. We don't even need these conditionals. I could remove this altogether, and I could now do as follows. I can rely now on menu to only give me a feed choice that is valid. And if I go back and source again, let me try now 7, I'll still see the same result, even though those conditionals are gone. So we've successfully now built a program to handle various user input and take the user down different paths depending on that input as well. We'll come back in a few minutes and see how we can combine data from different sources to also make a really large data set that we can answer questions about. See you all in 5. We're back, and we've seen so far how to remove unwanted pieces of data, how to find subsets of our data, and now we're going to see how we can combine data from different sources. Now, in one context, I might want to do this actually, can I do that again, Ramon? Sorry, I realized I didn't have the slides up. We're back, and so we've seen so far how to remove unwanted data values, how to find subsets of our data, and now we'll see how to combine data from different sources. Now, in one context, maybe you're actually working on that kind of problem, is going to be in, let's say, e-commerce. You can think of a giant like Amazon keeping track of all the purchases customers make on their platform. So here is a table that Amazon might have somewhere in their servers, and they might try to store the customer ID, some unique value for every customer, and they might try to store the sale amount that the customer actually, sorry, Ramon, can I do it one more time? We're back, and so we've seen so far how to remove unwanted pieces of data from our data frames, from our vectors, and we've also seen how to subset our data as well. Now, we'll take a look at how we can combine data from different sources into one big data set. Now, for this, we'll introduce the idea of an e-commerce kind of data set, where here, let's say, some giant like Amazon is trying to keep track of customers and the purchases that they made. So here in this table, every row corresponds to some purchase made on something like Amazon.com. Notice how every customer here has their own unique ID. And one identifies me, and one might identify you, but at the end of the day, every customer has their own unique ID. Now, for every transaction, every checkout on Amazon, for instance, we might keep track of the sale amount, how much this user spent on Amazon.com. So it seems like user 9971, they spent $29 when they checked out. User 7934, they spent $71, and so on. Now, when you have lots and lots of this kind of data, it might actually not be stored all in one table. It might be partitioned across several different tables, a bit like this. And it will be your job as the programmer to combine data from these different sources into one data set so you can answer and ask the questions you have about this data. Let's go back to RStudio and actually show an example of combining data from these different sources. So here in RStudio, I will create a program called sales, where I'm trying to combine sales data from different parts of the year. I'll name this file sales.r, and I'll create it. Now, if I go to my File Explorer over here, I'll notice that I have that program, sales.r, but I also have these 4 CSV files. It seems like one is called Q1, the other is called Q2, and Q3, and Q4. Now, we saw last time this idea of Q representing a question, like in a poll given to some potential voters. Here, though, Q means something different. If you're familiar with business, you might have heard of the fiscal year, kind of like similar to the calendar year, but the year in which they actually keep track of accounting and so on. Turns out that that year is broken down into 4 different parts called quarters, 3 months at a time. So Q1 stands for the first quarter in the fiscal year, Q2, the second quarter, Q3, Q4, and so on. So these are the 4 parts of the year of sales that this company had. Now, we were given this data in terms of each of those quarters. Why? Maybe a colleague just gave it to us like that. We need to figure out how to piece this data together now. So let's open up sales.r and see how we could accomplish that task. Come back to my computer here, and let me open up sales.r. And now, let me see if I can first read in each of these individual data files. Maybe I'll call the first one simply Q1 for the first quarter, the first 3 months of this fiscal year. I'll read the CSV called Q1.csv, and I'll do the same for Q2, Q2.csv, the same for Q3.csv, and now the same for Q4.csv, just like this. And now, if I were to run all 4 of these lines of code, top to bottom. I could do so with source, and I would see in my environment now, I would see that I in fact have 4 data frames, 1 for each CSV. Let's take a look at one of them. So I'll view Q1, and I'll see the very same table we saw a little bit earlier. I'll see customer IDs in one column and sale amounts in the other. Remember, every row here represents some purchase that was made from this commerce company. OK, so it seems like Q1 and even Q2, and even if we look at Q3 now, they all seem to have the same structure, the same number of columns, but perhaps different numbers of rows. And this is helpful for us. If we ever have data frames that have the same number of rows and the same names same number of columns and the same names of columns as these have, we can combine them using a function called rbind. Rbind is typed like this. It's literally the character R and then bind. And R does not stand for R, the language. It stands for row. Row bind. We're going to bind the rows of these various data frames into one big data frame. So rbind takes as input several data frames to combine via their rows. I could first give it Q1, and then Q2, and Q3, and Q4. And now, if I save this result in terms of its own object called, let's say, just total sales for the year, if I run this line of code on line 6, and I view, let's say, sales, I should now see that I have a really big data frame. And to prove it to you, let me go look at my environment over here. Let me make this a little bigger over here. You might notice that on the right-hand side, I have Q1, which of course had 2 variables, 2 columns. Same with Q2, Q3, and Q4. Each of these had roughly, let's say, 2,500 rows. But now, sales, that big data frame we made out of all of them, this one now has 10,000 rows. It's a combination of all the different sales we made during the entire year. So rbind and its sibling cbind are good for combining data frames along their rows, or in the case of cbind, along their columns. You can actually join data frames column-wise as well. So this allows us to take data from different sources and combine it into one. But what else could we do? Well, one thing I notice is that if I go back to my sales table here, the entire thing, I've lost a bit of information, namely in which quarter each of these sales occurred. Like, did they occur in quarter 1, or quarter 2, or quarter 3, or quarter 4? I don't know anymore. So we should probably be a bit careful about combining these, and instead first maybe add a column to each of these data frames. Maybe one called quarter that tells us exactly what quarter this sale was recorded in. So in the Q1 table, maybe I'll add this column called quarter. And recall from last time, if we want to add a column, we kind of wish it, quote unquote, into existence. I simply type the data frame's name, followed by a $, followed by the column I want to exist, and then I assign it some value. Now, in this case, I would love for the quarter column to just show Q1 for every single row. And if I want that to be the case, I need only type Q1 in quotes. And now, if I reread Q1 and run line 2, and now if I, let's say, view Q1, this data frame here, well, I'll see I have a new column called quarter, and throughout all the rows, I've set that column equal to Q1. So pretty helpful. But now, if I go back to trying to combine these data frames, what might happen? If I go down to line 8 now, I'll run line 8, and oops, I see an error in rbind, which tells me the number of columns of arguments do not match. And I think it's a little obvious what's happened here. So Q1 now has 3 columns, but Q2, Q3, Q4, these other arguments to rbind, those in this case only have 2. So we need to make sure we're combining data frames that have the same number of columns. We want to join them at least by row. So let's fix this. Let's go back to RStudio, and let's go ahead and just make sure that every table has its own column called quarter, and that that column is equal to whatever quarter the sales appeared in. So Q2 for Q2, and then Q3 for Q3, and then Q4 for Q4, just like this. Now I can rerun this code top to bottom using source. I see everything work just as well. And now when I view sales, I now have that other column called quarter that can allow me to differentiate between individual quarters now of sales. So helpful when I combine these data frames to keep track of where each piece of data came from. Now, one kind of last flourish here, if we can actually show us another new feature of R, is going to be trying to categorize this data. So we combined it, but one thing I want to do is figure out which rows were particularly high value sales. Maybe my boss wants me to figure out which customers were spending the most money. Well, I ideally would want to create a new column and have it be based on the values of some other column. For instance, let's say this is our table again, this one called sales. I still have the same customer ID and the same sale amount, but now I want to categorize this data to add another column that tells me whether a sale amount was a high value transaction or if it was just a regular one. So this could look a bit like this. Maybe I add this column called value for the value of this sale. And if it's over 100, I'll mark it, I'll flag it as high value. But if it's not, well, I'll just make it a regular old sale. And this could help me later on find a subset of my data that includes only those high value transactions and those customers who spent more money than usual. So let's try to actually add in this value column. And it turns out that to do so, we make use of those same conditionals we just saw. Come back to RStudio here, and why don't we try this? Ideally, I might create some kind of logical expression on sales. I would say if the sales, the sale amount column, is that greater than, in this case, 100. And if it is, well, I want to create a column that has high value for those particular rows, otherwise just regular. So let me run this particular logical expression, line 15, and I'll get back this really long logical vector. I see a few trues in there, so it seems like there are a few rows where you just spent over $100, but now my job is to create a vector that if this sale amount was greater than 100, shows high value, and if it wasn't, shows just regular. Well, I could use a conditional, but I could use a special kind of conditional that R has, one that works really well with vectors and producing vectors as well. This is called ifelse as a function now. Ifelse can be a function, and its first argument is going to be the logical expression to actually evaluate for every row. So here I have sales, sale amount greater than 100, and if this is true, my second argument to ifelse will be the value I want to see in the resulting vector. So I want to see high value here. And the third argument will be, what is the case that's not true, else in this case? I want to see regular. And now, with these three arguments, ifelse will return to me a vector where if this condition is true, I'll see high value. If it's not true, I'll see regular. Let's try it. I'll run line 15, and now I'll see a similar vector, but now all of those trues are replaced by high value, and all of those falses are replaced by regular. So it seems to me like this allows me to create some new column for my data frame. I could then assign this vector as a column in my data frame. I could say sales, $, and then maybe I'll make a new column called, we called it value before. I'll assign that vector produced by ifelse now to the value column in sales, and if I run this line and now view sales just like this, I should see that in fact I have this new column called value, and if I find particularly high value sale amounts, those are all flagged now as high value. Now, what questions do we have on this categorization of data using if and else as a function now? Let's go to Ahmed.
Okay, shouldn't we put is.na or is.null because might some variables be corrupted? But plus, I want to say something. Can I add in the end of lecture upload passage or upload to you CS50 staff with you, Sir Carter Zenke, and David J. Menon, Professor? Can I?
Let's focus on the question first. So the question, can you repeat it for me first?
Okay, it's a question. shouldn't we use s.na or s.null to write the code defensively, as if some variables could be corrupted in the list?
Yeah, so always thinking defensively, which is good. And it could be the case that in this data set, we might have some NA values, some values that actually don't have a number or a sale amount in them. We could actually try to improve our design using that kind of approach. I'll go back and do the same. I'll come to RStudio here, and like we saw before, maybe I should, just to be safe, go ahead and subset this data to make sure that I'm removing any values that are NA. So I could, for every one here, I could do Q1, and I could then assign it to be the subset of the Q1 data frame, where in this case, let's say the sale amount column is not NA, just like this. And I could repeat this, let's say, for every other quarter that I have, Q2, Q2 here, Q3, Q3 here, Q3 here, Q4, and Q4 here. And so although our program is better designed, like I would say we're removing those NA values now, I think there's a pretty big opportunity for improvement here. Notice how there's a lot of repetition. Like on lines 1 through 3, I'm doing effectively the same thing as on lines 5 through 7, and on 9 through 11, and on 13 through 15, but just with different Qs, Q1, Q2, Q3, Q4. Now it turns out there is a way to make this program even better designed. For that, we'll need some loops. And although we're out of time today, I think what we'll do is come back next week and learn more about these loops to help us improve the design of these programs and more. See you all next time.